Good morning and welcome to the video tutorial on TKGate. The desktop that you see on your screen is the one of the virtual machine provided by the University of Urbino to the students enrolled in the Laurea degree program in Applied Computer Science. TKGate is pre-installed and you can find it within the instruction submenu. And here is the link to the TKGate circuit simulator. The version of the circuit simulator is the 1.8.7, which is the stable version that is compatible with the Debian distribution. The virtual machine with the pre-installed version of TKGate can be downloaded from the website of the degree program, the URL of which is informatica.uniurb.it. Okay, let's start speaking about TKGate. TKGate is a CAD tool which allows us to design and simulate digital circuits. When we launch TKGate, a tutorial appears that contains already several circuits and also several different sheets containing different circuits which can be used to familiarize with the tool and also to exemplify all the features, all the main features of the tool. But right now we are not following this tutorial, rather we are trying to build our own project, a very simple project to start with. And to this purpose we need to get rid of everything and start a new project. So we have to click on this white page. We can call it new.v or EXOR.v just because today we are trying to build together an EXOR. Notice that the extension is V, which is the initial of the hardware description language, which is used to store all the components and the topology of the circuit that we are designing in the screen. So basically what happens is that even if we are playing with a graphical interface to add components and to connect a component to each other, the graphical interface corresponds to a topology which can be specified using a hardware description language. And this is exactly what happens, so that the result of our design will be a specification provided in this specific language. Okay, now we are ready to start. The first thing to do is to add components to this white page, and to this purpose I need to click on a point in the screen to go to the Make menu, to go into the Gate menu, and I can directly take an EXOR. As you can see, this is the symbol commonly used to represent an EXOR, and the EXOR has 2 inputs and 1 output. I could try to simulate this EXOR, but if I try to start the simulation, then 2 errors are notified because there are no gates driving the 2 input nets. And without knowing which signals to apply to the inputs, the simulator is unable to simulate the behavior of this gate. So let me dismiss this simulation and try to add also the input components. To this purpose, I click here and I go to the Make menu and to the Input-Output submenu, where I find several input and several output components. I take a switch, and then I need another one to be connected to the other input. To this purpose, I do something different. I'll right-click on this position so that the Make menu appears directly here. I go to Input-Output submenu and I take another switch. And then I connect the 2 switches to the two inputs. To this purpose, notice that I have to press here at the output net of the switch and to keep the left mouse button pressed and to get to the other end of the input net of the EXOR gate. Now let me try to launch the simulation again, and right now the simulation starts. But if I run it, nothing happens, just because there is no output component to make it apparent the behavior of this EXOR gate. So let me stop the simulation and add also an output component, in particular a LED. I connected the LED to the output of the EXOR, and now if I run the simulation again, as you can see, right now the two inputs are different. This takes value 1 and this takes value 0, so that the output is 1. If I switch the input, then the output switches as well. The LED has three possible colors. Yellow, which means undefined, and before starting the simulation the color is yellow, and then red, which means on, and light red or pink, which means off, as in this case. Okay? You can also notice that a scope appeared when I when I launched the simulator, and here we don't see anything, just because this scope is meant to represent waveforms of the signals, but only of the signals where probes are placed. And to place a probe in a signal, I need to double-click on a net when the simulation has been launched. And here is the effect. Right now we have three signals here, which are ready to represent the behavior during simulation. And I can play with the two input switches to make something happen in the simulator, and as you can see, the waveforms appear. I can zoom in a little bit and notice that the waveforms are like square waveforms, meaning that the rising and falling edges are perfectly vertical. And this is just because this is a logic simulator. So this means that signals are not meant to be electrical signals, but just logic signals, which takes a value 0 and 1, and the transitions between 0 and 1 and 1 and 0 are instantaneous. Also notice that if at some point, let me zoom in a little bit again. So right now, we are here at time 120. This is simulation time. If I switch off this input, let's see what happens. Let me go back a little bit here. Okay, we were at time 120 when I turned off the switch driving net W3, and this is the point at which this happened, and only after 8 time units something happened at the output, which is net W0. Also notice that at this point simulation stopped, even if I didn't stop the simulator. This is because TKGate is an event-driven simulator. This means that simulation time proceeds as long as there are events, scheduled events to be simulated. Input events are asynchronous in nature, so the end user, in this case, decides when to trigger them. So I can issue an event at any time, and as soon as an input event occurs, then the simulator simulates the behavior of the gate at the inputs at which the event occurred. But since there is a delay associated, the propagation delay associated with each gate, then the effects are not directly simulated, but just scheduled in the future. And in this case, an output event was scheduled after 8 time units, where 8 is the delay associated with this gate. And when this output event was eventually simulated, then there were no further events pending in the queue of scheduled events, so that the simulator stopped. If I want to resume simulation, I need to make something happen, or otherwise I can force the simulation time to go ahead by pressing this button here, which corresponds also to the space bar. And this is the effect. Okay. Now I can stop the simulation, and I right-click on properties to show you that the delay, the input-output delay of this XOR gate was in fact 8 time units. Okay, now we used an XOR gate to exemplify the basic functionalities of TKGate, but right now we want to build something and to make our own project. So let me get rid of the components used so far, and we want to build an XOR from scratch rather than using the XOR which is already provided by the simulator. And to this purpose, I want first of all to add a comment. So I go to the Make menu and I choose Comment to remind you which is the truth table of the XOR function. Okay. When both inputs take value 0, then also the output takes value 0. When there is at least, actually not at least, but exactly one input taking value 1, then the output takes value 1, and when both inputs take value 1, the output is 0. And this is the truth table, and we keep it here. Now, starting from the truth table, we are also able to find a Boolean expression corresponding to this function. Let me write the expression using another comment. I say that out is equal to the sum of min terms. The first min term associated to the first one is a prime b plus second min term, which is a b prime. Here it is. But we know also that there is a possible manipulation of this expression that, using De Morgan, can transform this OR into an AND. And to this purpose, I need to use this form here. So I recognize that this has the form x plus y, and that this is equal to x prime and y prime prime. Okay, so in this case this becomes a prime b prime ab prime prime prime. Okay, let me also keep this as a reminder, and this is the theory we start from. Okay, right now I want to show you that I can make a circuit implementing an EXOR which works exactly as the EXOR that we had before, using these two expressions as a starting point. And let me first of all make it by using the gates provided by TKGate. So first I use the EXOR again, and then I want to implement this function here. I use also the EXOR because I wanted to show you that the behavior of the circuit that we will build are exactly the same of the EXOR that we had originally. So right now I want to use the gates which are implicitly mentioned in this expression, which are two AND gates, two inverters, and one OR gate, and I connect, oops, sorry, them in this way. Okay. And in this last case, I recognize that this is an AND, this is another NAND, and the overall expression is an AND. So I still need two inverters, but in place of the AND and OR gates, I can use only NAND gates. There we are. Okay. Now I use LEDs to show the output signals. I connect the LEDs to the output of the three circuits, and then I use two input switches to drive all the three versions of the EXOR. So input-output switch, make input-output switch, and I connect the switches Oops, this is the wrong one. I want to connect this switch to the first input. Here we are. And I want to do the same for all these ones. Okay, and then I need to connect this other input. Here we are. Okay, now we are ready to simulate the circuit where we have two inputs, A and B. Okay, let me show you that I can edit the properties of this net and rename it A. I can call it B. I can also decide not to hide the name so that B appears here. I can do the same here. So A and B are now associated with these two nets, while those are three outputs of the three circuits which should implement exactly the same function. Let's try to simulate them. Here we are. We don't need the scope because we have the LEDs, and let's start the simulation. And as you can see, they take always, the three outputs take always the same value, meaning that the two combinational circuits that we implemented here, this one and this one, corresponding to these two Boolean expressions, implement exactly the same function as the EXOR provided as a native component by TKGate. Okay, so this is a first step, a quite good first step, but our project doesn't stop here because I want to show you something else. And in particular, I want to show you that I can make also a new component which is called EXOR, and within this EXOR I want to place some other components which actually implement it. So in practice, what I'm trying to do is to illustrate how to build a hierarchical project in which we encapsulate the complexity of a portion of a design within a block which can then be used as a building block for building more complex circuits. So to this purpose, I want to show you that we can go here and build a new module. So I take from the make menu a module instance, and I call it my EXOR. I resize it by stretching it from a corner, and then since this will have the behavior of an EXOR, I need to add inputs and output ports. To this purpose, I right-click on an edge of this square, and I add an input which is called A. Or, if we prefer, I can call it in1. Then I have here another one, add input, which is called in2, and those are the names of the two ports, input ports of the EXOR. And then on the right edge, I right-click in the middle to add an output which is called out. Okay, here is my component, and right now I want to make this new component work exactly as the original one and exactly as the two circuits that I had here. But before going ahead, I need to do something which is very important. So notice what happens if I select this component and I press here. This button in the menu means entering into this component to see the implementation or to provide an implementation. And if I press here, I find an empty page, which means that we do not have so far any implementation for this component. But notice, please, that into this panel, there are no ports. If I go out, I need, in fact, to select this component and to go to the module input and to press Set Interface to actually associate an interface with this module. Apparently nothing happens, but if I go inside this module again, now I find the ports. And within this component, I can now provide an implementation of the EXOR. And the implementation is the one that we already know. So we already provided an implementation, but this time we want to do something fairly different, because instead of using the native components, we want to build our own gates even within the EXOR module. So instead of using the components that we already have, we use other modules. Sorry, I didn't press here before actually creating a new module instance. And we need two types of modules. We need an inverter and we need an AND, because we want to provide the last implementation. So let me call it my inverter. And this will be a component with just one input and one output. So let me add an input here, which is called in1, and an output here, which is called out. And then I need also another component, which is my NAND. And my NAND is a two input component. So again, I have in1 in2 and out. Okay, now I select this component, my inv, and I go to the module set interface, and I do the same for my NAND set interface. Now what I can do is to create new instances of the same components. So if I press here and I take module instance, and if I choose my inv, instead of having a default square box right now, I have another instance of the same module that I already defined, or better, the interface of which was already defined. Now I can do the same for the other NANDs that I need, because as you probably remember, let me go up to show you what I'm trying to do. I'm trying to re-implement this using my own components. So we need 3 NAND gates and 2 inverters. So let me go inside again, and I need 2 other instances of this. So I can go here and say module instance my NAND, and here it is, and last time module instance my NAND. Okay, now I can connect the components in the proper way. Oops. Notice that if the components are properly connected, you can move them around and the connection is maintained. Okay. Now, at the inputs, I do not need to provide to use switches and LEDs because I need instead to connect these internal components to the interface ports of this module. So to this purpose, I go to the module, to the make and module submenu, and I take module input. And then I have to give to this input exactly the name that it has as a port of the component. Then I say that I want the name to appear, and this is the effect. Then I do the same for the other input. So make module input into, and here we are. And then finally I need to do the same for the output, which is called out. And here we are. So right now we have an implementation of this module, but this implementation is still missing the functionality. Oh, sorry, there is also a connection missing here. Because I used components which are still to be implemented. So let me click on my inverter and to go inside it. Inside it I find just the name of the ports, but there is nothing. And I wanted to go up to this point to show you that TKGate makes available also the transistors together with the gates, even if transistors are treated as ideal switches, so they are not electrically simulated but just logically simulated. But this is enough for our purposes because they allow us to implement the gates. So transistors are the most elementary components provided by TKGate, and they are special components that you can find within the gate submenu. So I take a pMOS and an nMOS, I use the pMOS to implement the pull-up of an inverter and the nMOS to implement the pull-down of a CMOS inverter. Then I need also to connect the pull-up to the power supply, and the power supply is called VDD, and it can be found within the input-output menu, and ground can be found here as well. So those are represent constant 1 and 0. Okay, now I'm ready to connect the two transistors together and to eventually connect them to the input port, which is here. And one. And then I have also to connect the output of the gate to the output port, which is here, out. Okay. Okay, done. Now I can go up, and remember that I entered within this module to implement it, but now if I enter within this other module, I find the implementation. In fact, what is nice is that once we implement a module, the module becomes yet another library component. So we can keep adding and using instances of the same module without having to re-implement it. So this is very, very, very useful as a feature, which is the main feature which allows us to keep the design simple, even if it is indeed pretty complex, because the complexity of each component is hidden within a module, and then it can be reused as many times as we need it. So let me do the same for the implementation of an AND gate. So I use CMOS technology again. I need, in this case, 2 pMOS and 2 nMOS transistors. We know that an AND gate is obtained by putting 2 nMOS transistors in series in the pull down and 2 pMOS transistors in parallel into the pull up. So let me connect them this way. Okay, then I need again the 2 constants which represent power supply and ground. I connect them. Here we are. And then the input ports in 1, in 2, and the output port called out. The output port is to be connected here, while the 2 input ports have to be connected both to the pull up and pull down. Okay. I'm trying to make the design as readable as possible, even if the graphical changes that I'm making right now have no effect on the simulator, of course. Okay, here we are. So this is an AND gate, and as we did before, we can enter into another NAND gate, to another instance, to double check that the implementation is the same. I go up again, and now we are ready to test our EXOR gate because we implemented all the components within it. So in order to double check that it works exactly as we expect it to work, we simulate it together with the other versions of the EXOR that we had before, and to this purpose I need to connect it to the first input, which is called A, and the other input to B, and I can run the simulation. Okay, the simulation has started without notifying any error. this means that from a formal standpoint, we didn't make any error, but it doesn't mean that it works properly. So to this purpose, we need to run simulation and to see if it implements the truth table. So let me check all the combination, the input combination. 0, 0, the output is 0. 0, 1, the output is 1. 1, 0, the output is 1. 1, 1, the output is 0. So our EXOR gate works properly. Okay, that's it for today. And notice that we did two main things today. The first one was showing the main features of TKGate. And the other one, which is, as I mentioned, an event-driven simulator. And the other one was exemplifying a top-down design approach in which, in order to redesign our EXOR gate, we first built a block without an implementation within, and then we entered this block and we created a structure which provides a first cut implementation using inverters and NAND gates, but the inverter and NAND gates that we used to implement the NAND-based expression of the EXOR were just empty blocks. And then we provided an implementation of each of them using transistors. So we implemented CMOS gates. So we started from the top and we went down to the bottom in order to implement the components that we already knew to be needed in order to resort to the overall implementation of our project. Okay, that's it for today. Thank you very much for your attention.